Hello, welcome back to another lecture. Let's do a problem on energy analysis of a control volume at steady state. What is a steady state? Take a look what I have on the board. Steady state, it basically tells us in our calculation that the mass flow rate at the entrance should be same as the mass flow rate at the exit. So I can make M1 dot is equal M2 dot. So what is m dot? And we did talk about that m dot is equal area time velocity divided by the specific volume. And so let's take a look at this problem. The problem states at steady state, we have this air duct that the air enters at a pressure of 200 kilopascal and a temperature of 325 Kelvin, and the entrance area is a 6 centimeter square, and the mass rate is 0.5 kilogram per second. And going through here, and the exit is going to be, the pressure is going to be 100 kilopascal, and the velocity is going to be 250 meter per second. And one of the things it can tell us basically here, there's no work or heat involved. So we can say basically our Q dot equal W dot equals 0. So we're going to use this equation to our advantage, try to figure it out. But again, we had another equation before we talked about, we said for ideal gas lab, PV is equal RT. And if we go ahead and calculate from specific volume from here, it's going to be RT divided by P. And in this case, we're going to be at the inlet, so I'm going to call it one here, one here, one there. So it's going to be T1, RT1 divided by P1. And we talked about that R is equal R bar divided by molecular weight. And we know that anyway, so that's given through a table. Another information that's given to us, it's a CP, which is right here. CP given as 1.008 kilogram per kilogram time Kelvin. So we have that information. And now we want to find out the velocity at the inlet. Let's go ahead and calculate the velocity at the inlet. We have all these equations right here. We can say m dot is equal to AV time divided by a specific volume. Therefore, if I go ahead and plug all this up, I can say that comes out to m dot, and that's going to be multiplied by plug in for V for specific volume, it becomes RT divided by AP. RT divided by AP, of course, this is going to be 1, 1, 1, and 1. And we already have all those information. Let's go ahead and plug in, see what we're going to come out. M1 was 0.5 kilogram per second. And then we have R. So R, I'm going to go ahead and just use what we have on, take a look at what I have on the board, is basically 8.314 divided by 2897. And 2897 come from the table for molecular weight. So I'm going to go ahead and say multiply by 8.314 divided by 2897. And let's put the unit in. The unit was kilojoule divided by kilomole and Kelvin. And the 2897 has a kilogram per kilomole. Okay, so I got M1, I got R1 now T, and T was 325 Kelvin. Okay, and that's it. Now I got to divide it by the right here, and I'm going to have A1. A1 is given as 6 centimeters squared. And P1 is given at 200 kilopascal. All right. The answer, the velocity is meter per second. So I'm going to say right here, V1, whatever comes out to, it should come out to a number, meter per second. And you look at this like, look like somebody got all this unit and put it in a can and shook it up and put it back in there. So, okay, go ahead and make meter per second out of it. Good luck to you. It's not that bad. Relax. We can fix it. So let's go ahead and delete some of this stuff. I got kilojoule. It's going to stay, not going to go anywhere. I got kilomole, cancel out with kilomole. Okay. I got kilogram, cancel out with kilogram. This doesn't want to work. We can find another one. And so those cancel out. I got Kelvin. With Kelvin, that's not good. No, Kelvin and Kelvin going to cancel out. There you go, because that's divided by Kelvin. I see no meter per second. So we got to fix this. What am I going to multiply by to unit to convert it? Take a look at the unit conversion table. See if you can find something from there. We know we don't want to do centimeters squared. We want meter. So let's convert this. So that means we want to have centimeters squared up here, whatever it is. And we would like to have per meter square. What is that conversion? You can look it up. It's like a 10,000, right? It's 10,000 centimeters squared per 1 meter squared. Okay, so that kind of canceled that out. That's good. I'm going to continue here. I'm out of room. Let me just erase this here. So I'm going to multiply, continue by, I took care of this kilopascal, and I got kilojoule. I got to take care of those. Kilopascal is Newton per meter squared. So 1 kilopascal is basically, that's on the bottom. Now we're going to put 1 kilopascal on top, and that's 1,000 Newton per meter squared. All right, so we took care of that, convert that, and I got kilojoule. So let's do a kilojoule. That's on the top. That means I'm going to go on the bottom for kilojoule. And we thought so we have 1,000 Newton meter is kilojoule. All right, now we can go ahead and our unit work out. So the trick was really to find out whatever we have is going to come out to meter per second. And we converted this to meter square, which we did. So that means this cancel out with this. And then we had kilopascal. We don't have a kilopascal here, so we converted that to Newton per meter squared. And then we had the kilojoule. We converted that to 1,000 Newton per meter. So let's see how it's going to work out. Kilojoule is going to go out with kilojoule. There you go. And Newton going to go out with Newton. Okay. 1 meter squared going to go with 1 meter. So I have per meter in here, but I got 2 over there. So this is going to be on top because it's per meter squared, it's the bottom, so it's going to come out on top. And those two are going to cancel out, so I'm going to have meter. I have meter left over and divide by second. And whatever this number is going to come out to, let's calculate that. 388.6 meter per second. So that was the answer to question number 1, which wanted to know what was the velocity at here. So we're going to say, okay, we found out the velocity came out to V1, came out to 388.6 meter per second. So for the question number 2, they want to know what is the temperature right here at this exit. But also they given us a Cp is equal 1.008 kilojoule per kilogram per Kelvin. Now, if you look at what I have, when we talked about specific heat, and basically Cp is the same as, let me write this down, Cp, it's the same as a dH divided by dT with respect to pressure, and we can almost translate this as a dH. So our dH is a delta H is equal Cp time delta T. We know the steady state for energy rate balance for one exit and one enters, one exit is given by 0 is equal, I have my equation, I'm not going to write it down, but it's 0 is equal. Now we have that, but of course we know that the these are 0, that's a 0, and we said that we ignore the potential energy, delta P is equal 0, so we remain with these two. I'm going to go ahead and substitute this in here, so in terms of H, M, we're going to have in terms of Cp. And that, therefore, we can say 0 is equal Cp time T1 minus T2 plus this right here, which is 1/2 V1 square minus V2 square. That's we go. And close that out. Calculate T2 from here. So I'm just going to become here, become positive. T2 is equal, divide both sides by Cp2. So I can write down T1 and become plus, plus because there's a Cp here. Just bring that 2 down. 2 Cp V1 square plus minus, sorry, V1 square minus V2 square. Plug in number. T1 was 325 Kelvin. 325 Kelvin plus V1 was, we just figured out 388.6. 388.6 square minus 250 squared. That's meter per second square when we do it, and then divided by 2 Cp. Cp came out to 1.08, so 2 times 1.008 kilojoule kilogram Kelvin. Great. Another unit conversion. So now this has to come out in Kelvin. This Kelvin going to come on top, so that's good. Got to get a kilogram, kilojoule, got to get rid of meter per second square to make that per Kelvin. So what we have for a unit conversion is, let me look at this here. So since we have a kilojoule right at the bottom, so we got to get rid of a kilojoule on top. I'm going to write this in a different color, and it's going to be like to multiply by, it's going to be a kilojoule in here. We know 1 kilojoule is equal 1,000 Newton per meter, time meter. And then the next one we have is the 1 Newton is what? We knew 1 Newton is 1 kilogram. It's 1 kilogram time meter per second squared. So meter per second squared goes away, kilogram goes away, Newton goes away, and kilojoule goes away. All we have left is Kelvin. And if we add that up, it should come out to 68.9. So we got 368.9 Kelvin. Okay. All right, before I go into the third, let me erase this board to get to the third question. Ready? 1, 2, 3. Pretty good, huh? You think I couldn't do it? All right. So now we this third question asking for what is the cross-sectional area at here. A2 is equal what? We don't know. That's a question mark. Anyway, so we have this equation here. We knew that M1 is equal M2. So we can, let's say, basically saying A2, velocity 2, and specific volume 2 is equal, and we can go ahead and say is equal to same way we did it here, be A2, which we erased it, is equal V2, and we want to replace it with specific volume, which comes out to P2, that goes on top, and divided by divided by RT, RT2. Okay, we found out what R was already. If we continue this equation, from this equation we can find A2. A2 is equal M dot 1 or M dot 2, which is the same thing, multiplied by, and we're looking for A2, then we're going to reverse the whole thing. So it's going to be R times T divided by V2 P2. Did I left anything else? I got V2 P2 down here. I got R2 they look good. Good. Let's go ahead and plug in. So A2 comes out to 0.5 kilogram per second. And then we have R, 8.314 divided by 2897. And of course, we got to do all this unit, which was this is a kilojoule, kilomole, Kelvin. And this one is kilogram, kilomole. Good. So we got that. T2 was a Kelvin, which was, we calculated. I know we did. But I just erased the 2. Was 368.9 Kelvin. Okay, I got R, I got T divided by, I'm going to divide it by, let me write that down in a little bit different color. And that is V2. V2 came out to 250 meter per second. And then multiplied by P2 came out to 100 kilopascal. So now we got to do unit cleanup. To do the unit cleanup is we're going to have, all right, the answer got to come out to, A2 got to come out to centimeters squared. So first we're going to go ahead and make centimeters squared. That means centimeter is going to be on top. So centimeter is on top. That means 10,000 centimeter. Just like last time was 10,000 centimeters square is 1 meter square. Okay. That's 1. Then we got to get rid of kilojoule right here. So we know 1 kilojoule is 1,000 Newton meter. Okay, I'm going to continue down here. So what else I have? I've got kilopascal. I got to get rid of that. So that means kilopascal has to be on top. So it's going to be 1 kilopascal is 1,000 Newton per meter squared. I left anything else out. Just check, see, make sure everything is correct. So Newton per meter squared, Newton goes, meter squared, 1 meter left, kilojoule goes, centimeter. Yep, they all check out. And that comes out to centimeter squared. But how much, I don't know. That is 21.2 centimeter square.